We can start. So good morning to everyone, and we are glad to have this morning Beatrice Bonga from Radboud University, and her talk is going to focus on the interaction between different black holes and how the interplay of their interaction can give rise to resonances that might be important in the central part of the galaxy in which we live or other galaxies. So I leave the stage to you, Beatrice. Thank you so much for our invitation. And
thank you very much for the introduction, Lorenzo. I am indeed very happy to finally be here. Sorry, last time I got ill. So this, I'm happy that the second time around I'm successful. So I am going to focus this talk on a very specific system called EMRIS, which is shorthand for an extreme mass ratio inspiral. So these systems describe, a central massive black hole of, 10 to the 5 to 10 to the 7 solar masses that is orbited by another small compact object. You can think of it as a black hole, but it could as well be a white dwarf or a neutron star. And this object, has masses between, 1 to 100 solar masses. Now, why am I looking at these systems? Well, for two reasons. One, we expect that we will observe these systems with the upcoming gravitational wave detector in space called LISA. And this is going to be, a very exciting system if we see them. Why is that? Because with these systems, we'll have extremely precise measurements of the parameters that describe this system. So in particular, we will be able to not just measure the mass of the central massive black hole, up to a few solar masses, but with, a precision of, 1 part in 10,000. This is incredible, right? Compared to the measurements that we have today of these black holes in these gravitational wave observations, we only see them, or the precisions maybe a few percent at best. So this is incredible, especially for astrophysical standards, mind-blowing. And also the mass of the central massive black hole is best constrained, but also the mass of the smaller object and the spin of the massive black hole can also both be constrained very well, probably with a factor of 10 less, but still, with 1 part in 1,000. So this really allows us to do all kinds of cool things, like, test this no-hair theorem about black holes, really probe the geometry of the central massive black hole, etc. And another reason why I look at EMRIS is, that these are an ideal situation to use black hole perturbation theory. Because in particular, this tool is now applied. And as a theorist, right, I'm always happy that whenever I can do analytical computations, I'll try to use them. So what people have done when they study these EMRIs, people have typically said, well, let's just model them as isolated systems. So, big black hole, smaller one, and vacuum everywhere else. And we asked ourselves the question, okay, how realistic is it? And what happens if, say, we have another small black hole or a neutron star or white dwarf nearby? Would that, change the dynamics, and would that change, the gravitational wave signature that we see? And of course, as a theorist, obviously the answer is if you put that second black hole very close, then clearly this will matter. But, then of course we want to put that at some astrophysical relevant distance. So what we did is we dug into the literature, and there are some, population models that suggest that, say, if the central massive black hole would have the mass of Sagittarius A star, then that next black hole, that perturbing black hole, should be at the distance of about 5 AU. In terms of M, this is about, I think, 150 to 200 M. So we said, okay, let's do, before we do any difficult calculations, let's do a back of the envelope calculation. So you can say, well, it's 5 AU. Perturbing black hole is really far away. So let's not.
Beatrice, sorry, I think there is some problem with the microphone. I don't know if I'm the only one that can hear it.
I could hear it as well. There was interference, yeah.
Yeah.
Still here?
Oh, it came back.
I have absolutely no clue what this is. I could.
Seems like a robotic thing, like.
You know what? I will connect with my iPad as well, and then maybe do the sound that way.
Okay. Okay. Sure.
I'll mute myself. And I'll continue like this. Okay. Luckily for all these extra devices, right? Okay, so we asked ourselves the question, okay, right, let's do this back of the envelope calculation. We can ignore, for this back of the envelope calculation, the GR effects, and let's just, do this Newtonian approximation of the strength of the tidal field, right? Which would just be given by the mass of the perturbing object times the mass of the central mass of black hole squared over the distance cubed. And here we put in an extra fudge factor of the cosine of the inclination angle, but that we can ignore. So let's plug in some concrete numbers, right? So let's take mass of Sagittarius A star for the central mass of black hole, put the perturbing object at say 30 solar masses and use that canonical distance of 5 AU. Then you get for this epsilon a number that is absolutely ridiculously small, right? 2 times 10 to the power minus 13. So at this point, one would say, clearly, you don't need to worry about this perturbing object. And you would generically be absolutely correct, except when you hit a resonance. So let me give you a one-on-one on resonances. So resonances occur when you have matching frequencies. So in this example shown here, right, you see a wine glass which has some natural normal modes, right, associated to the wine glass. And if you can sing very well and keep your pitch and match that frequency to the frequency of the normal modes of the glass, then you can get a very efficient transfer of the energy in the sound waves to mechanical vibrations. And this then can lead to a complete shattering of the glass. So when you have a resonance, this happens when you have a matching of frequency, and it can lead to sort of like quite drastic results. So now you may wonder, okay, what are the frequencies in the black hole scenario that are relevant for this? Well, as you may know, to describe an M-ray, we need 3 orbital frequencies. So if we look at the picture on the bottom right, we see that this picture looks somewhat, we see a random orbit of the small black hole going around the central massive one, even, ignoring the perturber. And we see that this looks, well, nothing like just the standard Newtonian Keplerian orbit, right? Which would just be an ellipse. And for that, all we need is just one frequency to describe the system. But as we know, because in GR, because of the strong field regime, one frequency is not enough when we need an additional 2. So we need these 3 frequencies. And that's exactly what you see plotted here. So for large distance between these 2 black holes, so for large semi-lattice rectum, you see that these 3 frequencies essentially become the same because you go to this Newtonian Keplerian orbit idea. But as you get closer to the central mass of black hole, right, when the distance decreases, you see that these 3 orbital frequencies are rather different. Good. So these are the frequencies that will play that role of the normal modes of the glass, so to say, in the resonance example. And now when you have a resonance, right, so typically if I were to describe, say, the evolution of the small black hole going around the central massive one, there are many variables I can use. And in particular, one of them is to look at, say, its angular momentum. So its angular momentum, will oscillate a bit, and it will, decay over time because of gravitational radiation, but it's more or less constant on very large timescales. Except when you hit a resonance. So when you hit a resonance, boom, you sort of get a drastic effect. And then after the resonance, again, it's more or less constant, although, the decay is much larger now because you're now closer to the central mass of black hole, and therefore you emit more gravitational radiation, so this decay is faster. Now, the resonance condition that you see here, that happens exactly when those orbital frequencies that I showed you become commensurate. So that means that whenever I multiply them by integers, so m, k, and n are integers, and they are 0, you get this resonance condition. So in the rest of the seminar, what I want to convey to you is like, why is this the resonance condition? How to calculate the size of that jump, and tell you whether this is detectable. Well, I guess you can already guess from the fact that I'm even giving this talk that it is going to be detectable. But quite surprisingly, right? Given the fact that this epsilon parameter was so small, right? 10 to the power minus 13. So let's dive right in. So for simplicity, we're going to build it up slowly. So let's remove that tidal perturber first, and let's just look at this Emery system by itself. There are many ways to describe the orbit of the small diagonal around the central massive one. And you can use, the usual coordinates or your Linkus coordinates or something like that, or you can use some conserved quantities. Now, it's quite convenient to use action angle variables. Now, because to zeroth order, we can say, well, this small guy, it's small, so small, we might as well treat it as a point particle. And we know exactly what point particles do in GR, right? They follow geodesics. So for that reason, right, this guy we can just think of as following a geodesic in the curved spacetime. And because the curved spacetime has all these nice symmetries, there are 4 constants of motion. It's the rest mass of my test particle, its energy along the orbit, its angular momentum in the z direction along the orbit, and the Carter constant. And because of these 4 constants of motion, the geodesic equation is completely integrable. And it turns out that these, as I said, these action angle variables are quite useful. So these actions, these j's, are conserved, right? They don't change as you go along the orbit, so they're 0. And you can just think of these actions as being some combination of these 4 constants of motion. And then we also have these angles, and these angles, they evolve at a constant rate given by these frequencies. In fact, actually, the frequencies that I showed you in the previous plots are exactly these frequencies. Good. Now, before I introduce a perturber, you say, wait, but the motion is not geodesic. I know this because of gravitational radiation, right? Because of gravitational radiation, the small object is going to spiral inwards and finally will merge with the central massive object. So you're right. So we can take that into account. And we do that in the following way. We say, okay, well, there is this nice smallness parameter called the mass ratio, right? Which is the mass of the small object over the central massive one. And it will change this fact, right? So these actions are no longer exactly conserved, but they slowly change, right? By this. Okay? This is a small quantity, so they slowly change. And also the angles will change, right? So they're not just evolving at with these constant frequencies, but they're also modified. Now, in principle, right, calculating these functions, they depend on all these parameters, is a rather difficult task, and it certainly can be done, but it's painful. Now, it turns out one can make a further approximation, so one doesn't need to know all the details of these functions, but one can make this adiabatic approximation, which is what people do when they calculate the self-force. So essentially what you do is you sort of do some kind of extended orbit averaging. And when you do that, it turns out that you don't even need to know this function at all, and you just need to know the average of this function. So what do we mean by that average? Well, averaging is quite nice and simple, right? Because these are proper angles. So they go from 0 to 2 pi, and therefore you can nicely use a Fourier decomposition. So we can write this Fourier decomposition as e to the power I k times these angles and n times the angle QR, right? Where k and n are integers. So in principle, right, this is an infinite sum. Now, when we average, right, we see that these terms all oscillate. Right? So typically when you say, okay, when you average, right, all the oscillatory parts should drop out, which is very nice. So when the parts that don't oscillate are, of course, the case where K and N are 0, right? Because in that case, I just get a factor of 1. So this averaging procedure tells me that I really, out of that infinite set of Fourier modes, I really only need the 0, 0 piece. So that's great. And this is generically true, except when you hit a resonance. Right? So when you hit a resonance, right, you see that this factor, right, will also not oscillate. In particular, right, its time derivative will be 0. Right? And the time derivative of this factor is just the frequencies. Right? So you get, right, K times omega theta plus N times omega R is 0. And that's why you see that this is the resonance condition. Just to get a picture, we can here look at the generic evolution of, say, there's the small guy go around the central massive one, projected in the XYZ plane. And you see it's rather messy, but if we now project this onto the R theta plane on the right-hand side, you kind of see this very nice structure that you sort of fill out this two-dimensional plane over time. This is for a generic evolution. Now we can also look at how this looks for the resonances. And then we see, we could look again at the left plot, and you may see that it looks less messy over time, but it's very hard to say something definitive by just comparing these plots in the XYZ planes. But if we project this again to the R theta plane, it's kind of striking what happens. Right? It doesn't matter how long I wait, I'm not filling out this two-dimensional plane at all, right? I'm restricted to this one-dimensional subset. And this is also the reason, right? My averaging is maybe not a great idea, right? Because when on a resonance, right? Because when you average, you sort of assume that you fill out this two-dimensional space, but we're not when you hit a resonance. Good. Now, this is the story, right? These resonances that I showed you actually happen already just for the cell force itself. So gravitational waves themselves can create resonances. And as you can expect, right, this can also happen when we have a tidal perturber. So we use, again, the action angle variables with, the cell force with these gravitational wave effects, and we add the tidal force, right, which is also nice because we have that smallness parameter, the epsilon, right in front of it. And there's one important thing, though, to note, right? So these functions obviously are both different, right? But there's also a qualitative difference, and that is that the cell force is axisymmetric, right? So it doesn't depend on the Q phi. And this is, of course, quite intuitive, right? Because the curved background space-time is axisymmetric, so therefore also it doesn't really matter sort of what side of the black hole you are, how many waves you emit, right? This should be independent of that. But of course, once I introduce a perturber, that breaks this symmetry, unless I were to put that perturber, of course, along the spin axis, right? But generically, this should then now also depend on Q phi. Okay, so let's go and do the same adiabatic approximation again. So we don't care about the average of the top function, and we only care about the average of this function below. Again, we do the same thing, right? We do a Fourier decomposition, and then we notice that, hey, because it now depends on Q phi, this Fourier decomposition also has this MQ phi term in the exponent, which means that now, right, resonance conditions occur whenever this is not changing in time. So whenever we have n times omega phi plus q times omega theta plus n times omega r equals 0, right? So we have sort of this additional direction in which we can satisfy this resonance condition. So this resonance condition is more general than for the cell force resonance. And in particular, it also occurs for low eccentricity orbits. So as it turns out, for the cell force, right, you don't have this phi direction. And when you have low eccentricity, right, you essentially don't have the omega theta. So then you just have one frequency, and you cannot really have a resonance with just one frequency. So in the case of a cell force, you really need some eccentric orbits to get these resonance conditions satisfied. But for us, that's not relevant because you have sort of a bigger space for this resonance condition to be satisfied. Good. Now, you may say, okay, great, this is very nice, interesting mathematically, but when does this ever really happen? Does this condition ever, is it ever zero along a resonance or along, a real trajectory? Is it just a mathematical curiosity, or does it physically also happen? And the answer is actually, in fact, many resonances occur during an inspiral. So in particular, what you see in this plot is, I'm looking at the trajectory of a small black hole going around a central massive spinning black hole with spin 0.9. And I'm giving it some arbitrary initial conditions. In this case, I'm putting it at like quite close already at a distance of 9m in terms of the semi-lattice rectum. And I give it some relatively high eccentricity of 0.7. And then, of course, what happens, right? We know because of gravitational radiation, you get closer to the central mass of black hole. So you go down this plot, right? The P decreases, and also your eccentricity decreases because of the Matthews-Peterson effect that you circularize over time. So we go down like this as time approaches. And then what you see in this plot, you hit all these surfaces, this surface, this surface, this surface, that surface. These are surfaces where the resonance conditions are satisfied for specific integers of mk and n, where I am just using mk and n being small. So I'm plotting cases here with mk and n up to integer 4. Why am I restricting myself to small integers? This is, or it has been shown somewhat generically, that whenever you look at resonances with low order integers are typically more important. This is not unique to the gravitational setup, but it happens sort of anytime you have a resonance. So we're restricting to sort of low integers because these are the important ones. Good. So many of them happen. Now that's nice, but then of course, okay, happen, but what's the size of the effect, right? Even if this resonance happens, but the size of the effect is really small, you still don't need to worry about it. So let's calculate the size of the effect. And there's two sort of equivalent ways of thinking about it. So we can say, well, this mu sort of follows a geodesic in the perturbed, well, ignoring gravitational radiation for the moment, but we can say this mu follows a geodesic in the highly perturbed spacetime, right? So this background metric of the curved spacetime plus the metric perturbation induced by this tidal perturber. An alternative way we can say, which is completely equivalent, is to say that this mu now is no longer following a geodesic in this curved spacetime, but is being accelerated by a tidal force that is, determined by this perturbing object. And that is the perspective we take. So now we need to calculate that tidal force. So how do we do that? Well, there's this very nice formula in the literature that tells you how to do that for a generic metric perturbation. And in particular, what are the elements of this formula? Well, it tells you that, of course, you need to take the Kerr background metric. You need to use your the tangent vector to your geodesics, right, the normalized tangent vector to your geodesics. And then you need to be able to take some covariant derivative of your metric perturbation. So for us, of course, this is the metric of a tightly perturbed Kerr spacetime. Also, luckily for us, that was already calculated in literature, so we just took that. And for the experts, that was calculated using the Tucholsky equation and then applying metric reconstruction afterwards. There did go some assumptions, of course, into doing this. It's very hard to do this generically, right? So the assumptions are that the tidal field is stationary, and that the dominant mode or the dominant contribution to this part is only the quadrupolar tidal field, so the L=2 mode, if you were to decompose it to spherical harmonics. Now, this stationarity assumption is valid, or is reasonable, as long as you have this following hierarchy of scales. So in particular, right, we should have that the orbital time scale is much smaller than the resonance time scale, right? So how long the resonance lasts, but also that resonance time scale should be a lot less than the time scale at which the perturbing object would move, right? So that the tidal time scale is still the same. So if the resonance occurs, and in other words, right, if the resonance occurs for some time, you want
the object, the perturbing object, not to move, right? So you want to say, okay, it's stationary over that time scale. And this is more or less satisfied, close enough satisfied for the configurations that we looked at. But it's definitely something to be taken into account. Good. So how then, if you do all these computations, what do you get for the jump size? As it turns out, sort of the jump size is mainly determined by two important factors: how long the resonance lasts, so its duration, and of course, how strong the resonance is, the resonance strength. Now, the duration is set completely by the radiation reaction time scale, right? This determines how long this resonance condition is satisfied. So if I emit more gravitational waves, so whenever I'm closer to the central massive black hole, the duration time scale is shorter. And when I'm farther away, the duration time scale is longer. Now, the resonance strength, of course, is set mostly by, all the parameters relevant to the problem. And as it turns out, that is the mass over the distance cubed of the perturber. So not these individually, but in this particular combination. And its sky location. So whether it's, say, in the equatorial plane or at some perturbed angle. The properties of the central massive black hole, so its mass and its spin, and the parameters of the embryo when it hits the resonance. So exactly, how close to the central massive black hole you are, what's its eccentricity, and what is its inclination angle when that happens. So when you take all that into account, you can actually calculate this jump, and that's what you see here. So here I'm showing you in the top plot an example of the jump in angular momentum and the Carter constant for a prograde orbit with this particular resonance, right? So when 3 omega r minus 2 omega phi equals 0, around a spinning black hole of 0.9, that is, at an inclination angle of 50 degrees. And as you can see, well, there's some numbers, you can calculate this. So here we calculate this for, these different parameters. And you see a fitted line across it. Now, of course, there's one important comment to make. This depends, this jump size that you see here is essentially the maximum jump size that you get across a resonance. Because if you remember, right, when we decompose this G function, we have this e to the power I and blah, 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 right, with the Q phi's. And you should really, so the jump size is also determined sort of by the initial Q phi's at your resonance. Right? So you can sort of, if you want, you can think of this Q phi, for instance, to expand it as Q phi at resonance plus omega phi times tau plus higher order terms, right? Plus tau squared, sorry, plus higher order terms. So this is all to say, maybe just to make it not too complicated, but it matters sort of what the exact phase is with which you hit the resonance. So you can go through a resonance and sort of have, the phase fine-tuned in such a way that you don't even get any jump at all, right? Where neither your angular momentum nor the Carter constant changes. Or you, of course, can have a maximum effect. So in the rest of this plot, I'm assuming the maximal effect and showing you, what is the result of a maximum jump. And but in principle can always be smaller. So a quick recap of the calculation in case you got lost along the way. So what we did is, right, we started with essentially with this tightly perturbed Kerr metric. We used that and fed it into the acceleration to calculate the tidal force. And in fact, this can all be done very nicely analytically. But when you do that, you get, with the help of Mathematica, of course. But when you do that, you get a rather big Mathematica file. And then to calculate the jump across a resonance, what you have to do is essentially do some integrals. That, Mathematica can no longer do analytically. So for that, what we do is we do these things numerically, right? So we look at specific parameters and calculate the jump size across a resonance, just as you saw for the last case. But of course, we can do this across parameter space and then get nice fitting formula. So we do have some sense of how these jump sizes depend on all these parameters that I showed you. So we have some sense of how to calculate the jump size. Then of course the question is, okay, what does that mean for the waveform? How can we calculate its effect? And the way to assess this, or a nice way to assess this, is don't build a waveform directly, but first look at its phase difference. So what's that? What we look at here is the difference between the omega phi of an orbit where I take the resonance into account and an orbit where I don't take the resonance into account. I really compare two orbits, same initial conditions, but one, I turn the mass of the resonance on, and one I turn it off. I compare these two, and then I integrate, all the way from the start of the resonance till the punch. And I look at what is this number? What is this, what is the resulting phase difference? And roughly sort of like a ballpark number to keep in mind for Emery's with Lisa, for typical, signals that we expect with some standard signal to noise ratio, we hope to be able to resolve, phase differences that are larger than 0.1 radian. So let's see what we get if we do this across the parameter space. So here I'm looking at a situation where I put the tidal perturber not in the equatorial plane, but sort of off axis. And I look at, a random or a resonance with, these integers -3, 1, 1 around a slowly spinning black hole. For different inclination angles of the Emery. So this is the x, this is cosine of the inclination angle, I should say. And on the vertical axis, we have different eccentricities whenever the resonance occurs. And we see sort of what this phase difference is. So anytime, right, the phase difference is larger than 0.1, it's observable, but this is on a log scale. So that means that everything larger than, this -1 is observable. In other words, everything, that's not this dark blue corner up here will be observable. Of course, right, to calculate this, I had to assume some parameters for, to calculate some explicit numbers. So I assumed, again, the same numbers that I showed you at the beginning, right? So with, well, actually even more conservative, so to say. So with the mass of Sagittarius A star, the perturbing mass and the mass of the Emery being 30 solar masses, and I put it, just to be conservative, the distance even twice as far. So not at 5 AU, but at 10 AU. And if I put the distance twice as far, right, remember that the effect scales with 1 over the distance cubed. So distance twice as far, this is already like 1/8 as small as what I showed you before. And this means also that this epsilon parameter, right, is now not just 10 to the power -12, but 10 to the power -14. Right, so here we see an effect with these Emerys that even though this epsilon is absurdly small, it still leads to observable effects.
Beatrice, can I ask you a question here?
Yeah, of course.
So is it easy to understand, if I understand correctly, so on the vertical axis is the eccentricity of the Emery, is that correct?
Correct.
So the only observable effects would come for low eccentricity.
So actually, no, the effect is higher for higher eccentricity.
Oh, I see. I misunderstood. So when you put the red box around the...
yeah, that's the part that's not observable.
Not observable. Okay. So let me then ask you the other way around. Why is it the larger the eccentricity, then you get a more observable effect?
Okay. Yeah, that's an excellent question. So the story is multiple ways. So larger eccentricities typically lead to more eccentricities, but of course, more resonances. But that of course doesn't, okay, so once you're given a resonance like this one, given integers, then of course it doesn't say anything about the strength of the resonance. So I don't have a very intuitive reason why this would lead to bigger jump sizes. Let me see.
Is there a connection between the eccentricity and how long in general it takes in the resonance?
Yes, it certainly is. So in principle, I've sort of fixed all the parameters here. Once you know the eccentricity and the type of resonance and your inclination angle, you also know actually at which p-value actually this resonance happens, right? Because, so I'm not showing you this p-value, but the p-value is typically more intuitive to see the scaling or the radiation reaction time scale. So typically smaller p-values at resonance means shorter time scales, but shorter resonance duration. But actually, I don't know how it actually scales with eccentricity. This is a good question. I'll have to think a bit more about this.
No problem. Okay.
No,
Thank
thanks. Good. So I think at least, at this point, right, we were convinced it's time to build a proper waveform model, right? This is clearly observable. So now what we should do is really take this into account when we do our data analysis. Now, just one quick note right here. Of course, I showed this plot to you for these very specific values at the bottom, but it's quite easy to get them for different values. You can just use this scaling relation, and that goes quite nicely. So anyhow, conclusion, time to build a waveform model. I will not go into the scheme, but this is just there to convince you that we actually thought about how to implement this nice thing. And what we then find is the following plot, right, which I actually showed you before. So how to think of this plot, right? Again, here I'm showing you the change in angular momentum, one of the ways to think about how to describe the orbit. And what we've done is now, instead of calculating these jump sizes for specific cases, we have actually done a full numerical analysis of this trajectory. So we used something that's called the oscillating orbit elements method. So what it does essentially, right, it just sort of solves the geodesic and the cell force and the tidal force at each time step. As you can imagine, that's incredibly slow. We do not want to do this across the parameter space. It is way too slow, but it is good sort of for us to serve as a benchmark, right? To do verify our results and understand exactly what's going on. So the red line is exactly sort of what you get from doing this numerical analysis. What we then sort of checked is that we also made a resonance model. We made two different resonance models, actually. One where we implement the jump that we calculated sort of semi-analytically, right? The jump size we have sort of across the parameter space. We implemented the jump with, just a step function, and also with sort of like a smooth transition. As it turns out, for data analysis methods, it doesn't matter whether you do this nice smoothly or whether you do it just with a jump. The methods will not be able to tell the difference, and the jump method is computation a lot faster and easier to work with. So from now on, we're going to work with just this jump model. Good. So let me again just quickly, for your overview, right? The oscillating elements methods, essentially, right? What we do is we take these analytic calculations with the metric and the tidal force, and then evolve the orbit numerically across the parameter space. So we don't do these semi-analytic computations, which are great across the parameter space. We do this, for a single orbit or a few. It's very slow, but can be done. And the results very beautifully agree, right, with our semi-analytic computations. Good. So now we have to do, of course, some waveform validation. So what we have here is two different cases. One where we created on the top part, you see a waveform model created with our waveform model. That's just the resonance model, where we just included this jump with this step function. And the one also a waveform with the exact numerical analysis. And the two agree extremely well. So this is good. And now let's compare our resonance model, where we turned off the mass of the perturbing object, so that essentially the mass or the resonance didn't occur. And we compared it to the case where we actually do take the resonance into account. And what you see very nicely here is, that the two waveforms are very different. We don't need any fancy data analysis tools to tell us that the waveforms are different. They are clearly, visible to the eye different. Now, there's of course one important comment to make. They're different, not exactly, when I look at the when the resonance happened and I compare it to waveforms, they'll still look very, very similar. This is, not, at the resonance time that I'm comparing these models, I'm looking, close to the merger, right? So close to T merger. So I'm looking, at this many, thousands of seconds before the merger. So it really needs time, like this effect sort of needs to build up. So the resonance is the small effect, but because we're going to see these MREs for such long times, right? So, for a year or two, or, because we see them for so long, right, this effect builds up, and these waveforms become more and more different. And that's the reason why, we can clearly see the effect of these resonances, even though, these epsilon parameters are so small.
Beatrice, may I ask a question here? Could you build a model or a waveform like a red one with the resonances without the resonance in the just in the parameter space of your MRE? Because you said I don't really need numerical statistical analysis to see they're different. That's true, they are very different. But if I can build without the resonance the same waveform, then how can you know that's really a resonance or not?
Good, exactly. So we did do that analysis, and which I'll show you now, right? So we said, okay, let's now actually apply this, right? We've now invested this time to actually build this model. Let's see, if it even matters for these MRE analysis. So MREs, in fact, the data analysis is rather complicated. I'm no expert on it, but I collaborated with other people that luckily are very good at doing this. And MREs are challenging, well, first off, because of the long signals, but also because they have many parameters. So in particular, these are just the intrinsic parameters, right? So the masses of the objects, the spin, exactly the parameters at which you start seeing the MRE, etc. So many parameters, including, our little epsilon parameter now, our tidal perturber. Now, what we did is we said, okay, let's compare two cases, right? We have a signal, right, with a resonance in it, and now let's go analyze it with a resonance model and, with our standard methods where we do not account for the resonance. And what you see in this plot, right, it's a busy plot, but the nice thing is the injected value is always sort of at the black line, and our resonance model is always peaked around it, so it nicely recovers the values. But if we don't account for the resonance, right, you do recover, also parameters, but they're not the correct parameters. So, again, statistically, we may be very good at determining parameters, but they're always off. And in particular, the nice thing is that we're also reliable, or we can extract this epsilon parameter well. So we do recover exactly around this, and we can, constrain it away from being zero. So this is also something nice, right? Because that really tells us that this is indeed, it gives us information on where this tidal perturber is and what its mass is. Now, the nice thing also is that typically, right, whenever you include an extra parameter, you lose statistical significance, right? It makes your analysis worse. But as it turns out, including this extra parameter, it doesn't really harm any of the others, so to say. What do I mean by that? Right? If it were to harm the others, then what you would expect here is that, the resonance model will be a lot broader, like it will be less constraining, but it's not, right? For most of the values, it doesn't change, except, for this maybe the Q phi, you see that the resonance model, right, is less good at constraining in this case, but it's a rather minimal effect. So let me conclude by saying, right, that these tidal resonances, I think, are important, right? I hope I convinced you of that. And whenever we have data with a tidal resonance, right, if we do not correctly identify it, well, I guess in the least worst case, we just maybe infer the wrong parameters, as I just showed you. Or, I mean, I think worse, we might actually end up concluding that general relativity is incorrect, whereas, all we did is not correctly model the astrophysics. That's really there. On the positive side, I mean, if we do, manage to correctly identify these resonances in our data, then we do obtain very valuable information about the environment near these massive black holes, right? We can constrain this epsilon parameter, which tells us something about the next black hole close to the M-ring, which is something that I think we have no hope of seeing any other way, right? Because that extra tidal perturber is very close to this central massive black hole. It's unlikely we'll see it with any electromagnetic observations, because it's very close to the central massive black hole, and if it is also a black hole, there's no way to really see it. And secondly, we're also not going to see it with gravitational waves, because one, it's too far away from the central massive black hole to have its frequency is off, so it's not in Lisa band, and also it's a little bit too weak, right? Because the farther away, the strength of the gravitational wave signal is also weaker. So that other object we're not going to see in any other way, except sort of through its influence on the gravitational wave signal of the M-ring. So I think this is very exciting, and I think it's time for us to build better models and understand exactly what's going on. And I think this is also particularly nice, sort of these methods that we've developed, they also help us analyze or understand self-force resonances better. So sort of the data analysis techniques and tools also apply to those cases. I would like to take any questions or extra questions at this point.
Thank you so much, Beatrice, for the very interesting talk. I guess now we have some time for questions, so you can raise your hand or speak freely. I see Carlos. Me and Carlos, I have plenty of questions, but me and Carlos already spoke. So maybe if someone has questions, can go first. Yeah, I see Haroldo. Haroldo, please.
Thanks, Lorenzo. Thanks, Beatrice.
I lost you, Haroldo.
For the very nice seminar. So can you hear me now?
Yes.
Yes, I think my internet is a little bit unstable, but okay. So my question is about the integrability of the perturbed case, because in the Kerr case it's integrable. Well, it's well known, and then well, you can introduce action angle variables, and then you can solve your problem in these very nice coordinates. When you introduce the perturber, you do that in a manner to preserve separability in order to use the action angle variables, or it's kind of more complicated?
Excellent question. So no, the separability is not preserved, even using these action angle variables. I mean, it would be incredibly special, right? Integrability is really special. So I don't think even one could construct, or it would be very special. I don't know if there is even a situation where you could construct a tidal perturber, that I don't know, located at a specific point such that it wouldn't be broken. But right, the KEM theorem, right, from like action angle variables and all of that related to telling you whether you have chaos and things like that, it tells us that you can still use action angle variables as long as your, I don't know, perturbing force in this case is not too big. And with this small epsilon, it is very convincing that it's not too big, so to say. So we can still use these tools, but things are no longer, integrable in that sense, but we can still calculate the trajectories.
I see. So you assume some that this perturber is small, and then I think it's kind of approximately integrable, right? Something like
Yeah, in that sense, yes. In the KEM sense, it is.
I see. So imagine that you have a case where it's extremely chaotic, then this technique would not apply, right?
Correct. If you were to get chaos, this wouldn't apply. Let me actually, this is a slide prepared for that. So indeed chaos, also known as the butterfly effect, could occur in principle, but what other people have shown using some post-Newtonian calculations. So not, we really do, well, we also use some post-Newtonian techniques, but our calculation is more general relativistic, so to say, than the calculations in these papers. But in those papers, people did sort of, by essentially just numerically evolving this three-body system, they found that chaos can sort of occur by just looking at the trajectories and looking how sensitive they are to initial data. But it always happens sort of when this epsilon parameter was larger than 10 to the power minus 8. Well, we are 4 orders away from that. So to us, it seemed fine to not worry about chaos.
I see. But I think that has something to do with that invariant torus when you have integrability of Liouville theorem. Somehow you have to guarantee that the orbits must remain on the torus or approximately on the torus. I think it's
that's correct.
Yes, this way I understand. Okay,
no, that's correct. So what we have done also. I didn't show you these plots, but we have looked at sort of Poincare sections. And if you look at these Poincare sections, they are sort of like still nice and well, they don't show any evidence of chaos. So we felt confident that we didn't have to worry about this.
Yeah. Okay. Thanks, Beatrice, again.
Thanks for your questions.
I see Nuno also.
Hi, can you hear me?
Yes.
Yes. Okay. So thank you for your talk. So my question is the following. So you assumed at some point that the perturber is stationary, right? So how does the detectability of these resonances will depend on this condition? So if you assume the perturber to be time dependent, would you be able to detect this in general?
This is an excellent question, which we are currently investigating, actually. So I don't quite have the answer yet. My expectation is that it's going to be a small effect. But my expectation is that we'll still be able to see these resonances, but that's sort of the tidal force, so to say, that we're using to calculate these resonance is slightly different, and therefore the numbers will be slightly different. With some luck, we might be able to sort of also constrain using the fact that the distance, with some luck, we might be able to constrain sort of the rate of change of the perturbing object, how fast it's moving. But I think, I think likely we will not be able to constrain that extra parameter, but we'll still see the resonance. This is my expectation, but I have no numerical.
Okay.
Yet.
Can I ask you, how are you modeling the time dependence of the perturber?
Good. Yeah. So as of now, what we've started to do is just model it as it being in a Keplerian orbit.
Okay.
And then we're using first by Eric Casson, who has calculated sort of these, perturbations of tidally perturbed Kerr spacetimes, also taking into account, actually in his case he uses Schwarzschild, but then taking into account the motion of the perturbing object. So this is something we're currently investigating.
Okay, thank you.
Carlos.
You had to wait a long time.
Well, that's okay. No, I'm happy for the people who have questions, but I was curious about one thing. Well, first of all, again, thank you very much for your talk. I think it was very interesting, and very interesting physics. The point of your talk, I guess, or one of the main points is that you may think a perturber has a very tiny effect, but at these resonances, it's not, and therefore it can lead to these important effects detectable even. And this happens at the resonances, which, at least to leading order, are determined by the unperturbed background, that is the curve, right? So the resonances are properties of, which means that at a resonance, it's not a specific perturber that becomes relevant. All perturbers become relevant somehow. So then the question comes, of course, you're dealing just with one, but well, in any astrophysical environment, one might expect that there will be a bunch of things around a supermassive black hole that could, constructively or destructively, add to this effect. I mean, of course, the parameter estimation and all of that, this will be important. So my question is, first, do you think it's astrophysically realistic to isolate a single perturber? And two, how would you approach a more complicated problem of kind of an environment of perturbers?
Good questions. Yes. So I think it certainly is astrophysically relevant that there are more perturbers. Now, there's one important thing, of course, and that is that this effect scales with like mass over distance cubed.
Right.
So, as only really the closest perturbers are relevant because it's so sensitive to the distance. And in that sense, I don't expect there to be that many. So maybe indeed one is not enough, but we need multiple. But hopefully nature is kind to us, and there will not be too many, because I think indeed that would be. Well, that would not be good, so to say. Too many resonances is not nice. Just with a few, ideally. Well, and if that's the case, indeed, what I also showed you here is really just the effect of one resonance. But even if I have one perturber, I in fact actually expect multiple resonances to occur, even for one embryo, right? As I showed you sort of in that plot where you cross multiple resonance surfaces. Mm-hmm. Now, the later resonances are typically the less relevant because the duration time scale is so short, so you may not really worry about them. But in any case, it's likely that you'll at least have to worry about, 2 resonances for each embryo. That is, I think, still handleable, or we can still do with the data analysis. In particular, one should sort of come up with a consistent model where you say, okay, well, if you had a resonance there, then I know where the next resonance is, what its effect should be, and sort of one can come up with consistency checks, so to say. But this is something we haven't implemented yet. But that, in that case, I'm hopeful.
Okay. It's quite impressive already. But of course, one thinks ahead, and yeah, that would be a natural question. So thank you very much, Beatrice, again. Thank you.
Is there some other questions in the audience? I don't see more questions, and I can make maybe a couple. So first of all, thank you so much. It was very interesting, and even pedagogically, how you explain everything. So, which is the range of space where you are evolving this perturbed geodesic motion? Let's say you're from the horizon of the central black hole up to where you can model this thing.
The perturbing object or the evolution of the embryo?
The evolution of the embryo.
So for the data analysis, or these things, we started. Oh, this is a good question. I think around maybe 15 or 20 m, and then up till. Actually, we don't go all the way to the horizon, but sort of like to the ISCO thing.
Yes, yeah. My doubt is there because the metric that you're using for the Kerr tidal black hole is built on the metric reconstruction that is built above the Kinnersley tetrad, and shows, if I remember correctly, in the original paper of Younes and Gonzalez, they show that their metric reconstruction is good up to 4 or 5 m. with some 10% of error. So if you build farther away, is there some physical argument to say that the metric is fine up to 20 m?
Good. So good. I actually remember the details. I think what we did is we did check that sort of whenever the resonance happened, it is in the regime where the metric perturbation is valid. I don't remember the full number, but I think it was.
They say 4.5 m. That's
Okay,
why I was wondering, because it's very 4.5 m is very close.
It's very close
to the horizon.
So that is a very good point. So we also have compared with the Yunes-Gonzalez metric is really using, or it's quite complicated, right? And it looks rather messy because but we have compared also to the case where you just look at Schwarzschild perturbations or perturbations of Schwarzschild. And it turns out that, well, all the results are not super sensitively dependent on the spin. And there, everything is sort of more handleable. And it turns out that the results are pretty much identical. You do need sort of the spin. The spin really matters sort of for the evolution of the M ray, sort of what kind of orbit it takes, but it doesn't really matter for the perturbation, so to say.
Okay.
And
that's nice. Also because their metric don't have a equal zero limit, because it's subleading in the Poisson expansion of the multiple of the perturber, if I recollect.
Yeah, correct.
Okay.
So and then with the Schwarzschild thing, right? We don't have any of these issues with the Klinner-C temperate or whatever. So these problems do not exist. And that's why I'm also confident about these.
Sure. Maybe I just have our last question that might be less technical and more interesting for everyone. You started saying epsilon in our galaxy is about, let's say, it cannot be more than the power 13, if I remember, something around 10, at epsilon to the minus 10. So is it possible that, I don't know, in other galaxies, instead of having one central black hole, you might have a binary or something more tight, so epsilon can be pushed to higher values?
Yes, I certainly, right? But yes, so this is in a way actually more a question of astrophysicists, like, you know.
Yeah.
This is to happen, but you know, this 5 AU, it's sort of I know an average or an expected distance, but I guess one could imagine systems where, you know, the configuration is just different or something, or you know, some object got captured or whatever. Like, you know, one can expect that statistically that this would also happen, and that epsilon is about.
Yeah, okay, the question might be more like, is it possible that there is a physical environment in which even without the resonance, the effect of the third body is important for waveforms?
Well, that's a great question. So to that, I like that question.
So because with 10 to the power minus 13, I guess the answer is no. But if you can make it 10 to the minus 6, maybe.
So certainly, okay, so right, all the analysis I did is I am really relying on black hole perturbation theory, etc. So really what I want is sort of like a hierarchy of skills to do this analysis. But somehow if I sort of let go of this hierarchy of skills and still assume that everything applies, then I certainly expect that in the future we'll see sort of these triple systems, because for stars, there are in fact many triple systems. Like I already forgot, but I was sort of blown away by the percentage the astrophysicists told me that we have. So, I mean, in that sense, I expect there to be, you know, these triple systems with, you know, maybe more similar mass skills. And then, you know, if these resonances still apply, then I you know, this idea of resonance still apply, then or you know, I guess you don't even need resonances, because the perturbing object is so close that it will really alter the evolution. So I think the answer to that is yes, absolutely.
Yeah, cool.
It's just like our tools don't really allow us to calculate that. So
Okay, very good. Okay, thank you so much. Guys, if there are no final comments or questions, I guess we can give a big round of applause to our speaker. And thank you so much for being with us.
It was a pleasure.
And everyone, have a nice day. Bye-bye.